Yes, okay. So anyway, there's no issue. So this is the value of S, of course, that is the repeated root. Now the question, why I stopped getting confused for a second, is that all I'm trying to say is for which value of C is this term 0? So if we take a look at it, we'll say, okay, if I equate this to 0, I get C over 2m is equal to the square root of k over m. Therefore, I would say that the value of C, and let's call it C critical, the value of C that makes this equal to 0 is simply 2m times the square root of k over m, right? All right, so it is common to designate the square root of k over m as omega, and it'll be obvious why in a second. So we have that C critical is 2m omega. In other words, when C is equal to C critical, this radical is 0, and the roots are, it's only this, right? Plus or minus 0. And that's why we say there's only one root repeated. Why is it repeated? Because the derivative of the polynomial, which we saw is here, is also made 0 by that same root. This, okay? Okay, so we have then the situation that this is the dividing line. Now, this dividing line, 2m omega, we can then write that, I'm going to take this, I'm going to erase here because I get confused with so much stuff on the board. Okay, so we have C critical and we have this. Now, what we want to do now is to say, let's give a name for the sake of simplicity. What is the value? Let's call any value of C over C critical the ratio of C. This is the Greek letter squiggly. I draw it like that. It's not really the most precise sketch, but too many years doing it, that's how it comes out. So this is the letter C. Now, if we call C over C critical this, then we obviously can refer to C as simply being C times C critical, okay? And we've already said that we're going to say that omega is the square root of k over m. That is, up to this point, just a definition, with C critical being 2m omega. Now, if we do that, then we have that we can write S1, 2 equals C. Let's see, how do I say this? This C is equal to this times C critical, and then it's divided by 2m, right? So, and we have that C critical is 2m omega, so this is divided by 2m, and so you can see that this should be C over 2m, I'm sorry. I'm trying to simply look at this term here. So C over 2m is equal to this over 2m, which is equal to this. Okay? So I can write minus omega C, plus or minus, and then the square root of C over 2m squared. That's obviously the same as this. So I can just say omega C squared, the minus won't matter. I'm sorry, there's no minus, C over 2m squared. And then we have minus omega squared, right? So we see that the roots of the polynomial in general are minus omega C plus or minus. And then we can take an omega outside of that, and then we get the square root of C squared minus 1, right? All right, so I will erase again to give myself room. And we are at a point where we are saying these are the two roots of the polynomial that we have to make zero, right? For the solution of the free vibration. Remembering that we just said Qt is equal to A e to the st. And that we had cases in which either this term is zero, right? In which we have a real root repeated, or this term is less than zero, which this becomes imaginary, or this term is greater than zero, which becomes real, and we have two different distinct real roots. Okay, so let's take a look at the most common case first. And by overwhelmingly, the most common case is that C is less than 1. Doesn't really matter that it's much less, but this is the common situation. Remember that C is simply C over C critical, so it's just a way to specify how much is the damping constant in terms of a damping constant that is given by this, right? So let's take a case C is less than 1. That's usually referred to as underdamped. So if the C is less than 1, then this means that this number here is imaginary, right? And so we can write that in that case, we can write S12 is equal to minus omega C plus or minus, and then it's better to write it 1 minus C squared imaginary. Oops, with an omega here, right? Change the order, and then I put an imaginary in front. It is common to call this term here omega d. And the physical meanings will become evident when we finish the solution of the homogeneous response. But anyway, we give that name omega d, and then we have two roots, S1 and S2 being minus omega c plus or minus omega d I, where omega d has that definition, omega times the square root of 1 minus c squared, and we are working in the case where this is less than 1. Okay? So after all that discussion, elementary discussion, we know that the values that work here have that form when c is less than or equal to 1. So let's just plug them in. Because there are two roots, we know from our differential equation theory that we should write one constant for one root, minus omega psi plus omega damped I t, and another constant for the other root. So plus b e to the minus omega c minus omega damped I t, right? And so that's the solution that we have. Now from fundamental basic algebra, right, we write A times e to the minus omega c t times e to the omega damped I t plus b e to the minus omega c t times e to the minus omega damped I t, right? So it looks like that. Therefore, we write Qt is equal, this is common, right? This is a common factor on both, and so we have e to the minus omega c t, open a bracket, a e to the omega damped t I plus b e to the minus omega d t I, close that bracket, right? So we are at that point in the solution. I guess I can erase, because you guys can always rewind if you need more time to look. So I do this, and we are at that point. I guess I can erase this now. It doesn't really help us anymore. So we are here. Now we go and we call on our friend Euler, which is going to give us the sine cosine version of the exponential raised to an imaginary. And so we get qt is equal to e to the minus omega ct, open this bracket, a, and then we have this, which is what? Cosine of omega dt plus I times the sine of omega dt. And then we have b times cosine of minus, but the cosine of a negative angle is the same as the cosine of a positive angle. So cosine of omega dt, the sign does change, so it's minus I sine of omega dt, right? Close this, close the bracket. Now, we have that as the solution. So let's see what can we do. So we have qt is equal to e to the minus omega ct. Open this bracket, then I have cosine of omega dt is a common factor of a plus b, right? And we have plus the sine of omega dt, and that looks like that's a minus b, and that is an I here. So we are at that point, right? And then I will erase here. Okay, so we have that. Now, the solution qt is actually the vibration of the single degree of freedom system, must be real, right? Cannot have imaginary parts. Therefore, we conclude that a plus b must be real, and that a minus b must be imaginary. So that a minus b times imaginary, imaginary will just switch the signs, right? So we conclude that a plus b must be real, and a minus b must be imaginary, right? So I can write it like this. I mean, I can say if I call a real plus a imaginary I, then I can say that b is also a real minus a imaginary I. That way, a plus b is real, a minus b is imaginary, right? I guess there is a little bit of a flaw here that I just noticed right now. Now, it's not really a flaw in the fact that there is an error, but I mean, you could make the argument that of why did I use a real here being equal to this one. This one has to be the negative of this one, so when we add, no, is that right? A minus b has to be imaginary. Okay, well, let's just go forward. I'll think about it. It's not really very important, but anyway, if I write it like that, then I can say that a plus b is just going to be 2a real, right? And a minus b is going, actually, that's what I'm saying, it doesn't really matter. A minus b is going to be, change the sign of this and add them. So that means we would get 2a imaginary I, right? Now, in that particular case, then I can write this thing and say qt is equal to e to the minus c omega t. Yeah, this is why it was bothering, because there wasn't really a necessity of making that restriction. But a plus b is just a real constant, which in this case, let's say, is 2ar. And then we have here sine of omega damn t. Let me leave the sine away. Sine of omega damn t. And then a minus b is 2ai, right? And then I times I would be negative, so minus 2a imaginary sine of omega damn t. And it looks like that, right? My error, not my error, my slip on making that substitution is that all I can gather from this, all I need to gather really, is just that a plus b is a real constant and a minus b is an imaginary constant. I didn't even have to make them, you know, they're arbitrary. So I could have just simply jumped, instead of making all that argument, to the fact that because I don't care about the 2, this is just a constant, and I don't care about the 2, this is just a constant, I don't even care about the sign, right? I just simply say this is a constant C1, all right, and this is a constant C2, which is, you know, with the I cancelled and so on. And so what we have is, in the end, that qt is equal to e to the minus sine omega ct, parentheses, one constant, multiplied times cosine of omega dt, another constant, multiplied times the sine of omega dt, right? That's it. So I didn't need to do the a equals a whatever, right? So this is the form of the solution for the case when we have that this was less than 1, right? The value of the constants C1 and C2 are going to come from initial conditions, right? Or from, actually, we say initial conditions, but what we mean is from anything that has to be known about this. Doesn't really have to be at t equal to 0, but I need to know two things in order to get those two constants. Typically, we say, okay, at t equal to 0, which is arbitrary, which is at some point we happen to know that q is equal to q0, and so we just say q0. Now e to the 0 is 1, cosine of 0 is 1, sine of 0 is 0, and so we immediately find that the constant c1 is q0, okay? Now, at t equal to 0, we also know, let's say, the velocity. We could know actually the displacement at another time, but let's just say we know the velocity at t is equal to 0, so we say q0 dot is equal. Now for that we have to take the derivative of this. So first we have minus omega c times e to the minus, actually wait, let me just first be more precise. I'm just not at t equal to 0 this. Now this is just the velocity, not at t equal to 0 in general. Differentiating, we get minus omega c e to the minus omega zt times the bracket. I'm not going to replace it with all that stuff, but that means c1 cosine omega t blah blah blah, and then plus e to the minus omega ct, and then the derivative of this is just going to be omega d, right? And then minus c1 sine of omega dt plus c2 cosine of omega dt, right? Close that bracket. So that's the derivative of that stuff. Now at t equal to 0, if we say that q dot is equal to q dot 0, we have minus omega c times 1 times the bracket, but the bracket at 0 is just c1, right? Because this became 0, and then the next term is plus, this is a 1, and we have omega d, and then the bracket is 0 here, and then c2. What do I have there? Cosine, yeah, hard to read. Cosine, yeah. So this is a 1, and so we have omega d times c2, right? Like that. Okay, so I can erase this. And then we can put for C1 Q0, and we have something like this, right? So from this one here, we find that C2 is equal to Q0 dot plus omega C Q0 divided by omega D. So we have the constant C1 and we have the constant C2, right? And therefore, we can substitute and find that our final equation is Q of t equals e to the minus omega c t Q0 cosine of omega dt plus C2, which is plus Q0 dot plus omega c Q0 divided by omega d times the sine of omega dt times the sine of omega dt, and then we close the bracket, and then we're done. So that's the solution. That's the solution of the equation for the homogeneous case for z less than 1. Okay? Now, let's look at it quickly from the point of view of the physical significance. Because e to the minus omega ct is common factor of all this thing, we see that this is a decaying exponential. So that means that the solution that is inside this thing gets multiplied to something that starts with a 1 and it's decaying like that, right? This term looks like that with this being time. Right? So this, the higher this term, the higher this denominator, the faster this thing comes down, right? This term here is entirely harmonic. It repeats itself over and over and over, right? And we can see that the frequency that governs this term, that is, you know, the thing that governs how this is varying, is omega d. And that's why omega d is called the damped frequency. Okay? Omega d, you remember, is equal to omega times the square root of 1 minus c squared. When the damping goes to 0, then omega d is just omega. So omega is actually the frequency of the vibration of a single degree of freedom system when there is no damping. When there is damping, then the frequency of vibration is omega d, and it's related to the undamped like this. The fraction of critical damp, this is called the fraction of critical damping. Why? Because it's defined as C over C critical, right? And C critical, I remind you, was 2m omega. All right? That's pretty much all that can be said or should be said or about the homogeneous solution of the single degree of freedom equation. Let's see, what can I add, if anything? Oh yes, in practice, the value of C over C critical for typical structures is quite small. So actually typical values of C would be, let's say, around, you know, 0.02 for steel structures. So if you have steel structures, they would tend to be on the order of 0.02. That's the, you know, it's not a rule that has to be. It depends on various things, but basically that's a reasonable number. If you have concrete, the value tends to be more around 5 percent, right? So you see they're all kind of small. If something is highly damped on typical structures, it would be something like wood or masonry. And wood and masonry, you know, would be, you know, typically around 8% or something like that to 10%. Wood structures, I mean, not wood, wood structures, right? Or masonry, masonry structures. Could be like that, right? There, of course, are other structures that could have even less than 2% of natural damping. So when you look at the difference between the damped frequency and the undamped frequency, you can see that they are very, very close to each other. Because, for example, for a steel type structure, or for concrete, even for concrete, you would be saying that this is the undamped frequency times the square root of 1 minus. And now, you know, even this is 0.05 squared, right? You can see that that is pretty close to 1, right? In here. So a lot of times when people are talking, you know, outside of academia or something, I'll just say the frequency. And they don't even, you know, say the damped frequency or the undamped frequency because they're so close that it's, you know, who cares? It's essentially the same thing. Okay, so let's see, anything else? Yeah, that's it, right? So this is the form of the homogeneous solution. Now I'm going to stop the tape and start on the next section of the lecture to look at the response. Oh no, I'm sorry. Wait, before I do that, no. Before I stop it, we can take a look now at the solution when the damping is critical. I almost forgot because we have so little cases where the structure has, well, actually almost never, but let's say that the damping is critical. Because remember, we had this could be less than 0, that's what we just did. This could be greater than 0, we have not done it. Right? And in the middle we have actually not less than 0, less than 1, which is the radical. This could be greater than 1, and then this is the dividing case where this is equal to 1. So when this is equal to 1, we say we have critical damping. Right? Or simply that C is equal to 2m omega. C is equal to C critical is equal to 2m omega, so the fraction of critical damping is exactly equal to 1. So in this case, remember, the roots S1 and 2 would just be minus C over 2m, right? Because it was plus or minus 0. Because the square root is 0 at critical damping. So the root is the case of the repeated one, and that's S12 equals, and C is equal to this, so dividing by 2m, we get minus omega, right? All right, so we got the root repeated at minus omega when the damping is equal to the critical damping. In this case then, our solution, which I remind you we wrote like this, you may or may not recall, I hope you do, from somewhere in your background, that when you have this form and the root is repeated, then you have to write the solution like this. Let's just say CS because it's the same. Right? Because of the repeated root, then you have to do this. Now, so we basically have that QT for critical damping is equal to S is equal to minus omega, so it's S to the minus omega T. and then it's A plus BT, right? And so this is the solution for critical damping. And in order to find the constants A and B, we do the same thing as always. At t equal to 0, we have Q is equal to Q0, which is equal to A. So we get the constant A right away because t is 0 here. Now Q dot, as a function of time, is equal to minus omega c e to the minus omega t A plus bt, right? Plus e to the minus omega t times the derivative of this, which is just b, right? So now at t equal to 0, we get Q dot 0 equals, then we get minus omega c times A plus B, right? And we already know A, which is Q0. So then Q0 dot is equal to minus omega c Q0 plus B. Therefore B is equal to Q0 dot plus omega c Q0. Okay? And then we can substitute here to complete our process, and we have that Qt is equal to e to the minus omega t times A, which was Q0, plus B, which is Q0 dot plus omega psi c Q0 multiplied times t close, right? I will check in a minute to see if I didn't make a mistake, but I think not. And so this is solution when the damping is, the fraction of critical damping is 1, that is, the structure is critically damped. Okay, now this solution is one in which we see there's no signs on cosines. So basically what that means is that if a system has critical damping and you release it from some point, maybe even with an initial velocity, it'll go like that, right? It does not cross the 0, right? So it comes to rest. Now, if we look at the case with no velocity, so it's easier for me to draw it, that means that this thing would go like that. It's just this term, you know, if I have no velocity, well, anyway, it's this term just decaying. If the damping is greater than 1, you get the exact same thing, except it just decays slower, right? You still get no crossing, just slower decay. All right, let me pause this for a minute, and then we start with force vibration.